Hey guys, this is video 5.4, Drawing Covalent Bonds Part 2. So we're going to pick right up where we left off with the other one. I know this is longer. There's just a lot of information here that is going into drawing these covalent ones. These covalent ones are the ones you'll probably have to draw more so on the regents, so we got to make sure we spend a lot of time practicing this. So up until this point, we had seen every structure ran out of those electrons right when we needed them to. Okay, when they were on the last atom, everybody else was satisfied. But what happens if too many electrons have been used, meaning like, hey, we run out of electrons before everyone, oops, can't write, everyone has 8. Okay, what happens then? And that's what we're going to look at here in this video. And this is where we form multiple bonds. Okay. Now, one thing I will say, so this is like your double and triple bonds. Apparently, I can't write here today. Okay, so you're going to form multiple bonds. And again, this is a last resort. It's after you have, oh my goodness, after you've run out of all those electrons that you accounted for in the beginning. So same process to figure it out. We've got 4 electrons from carbon, plus 2 times 1 for hydrogen, plus 6 for oxygen. That's going to give us a grand total of 12 electrons that we've got to use in our structure. Same thing, draw your skeleton structure. We've got carbon as the center one, hydrogen, hydrogen, and oxygen. Now again, in the next video where we start talking about VSEPR, valence shell electron pair repulsion, we'll redo and fine-tune the structures. For now, I just want you guys to get in the habit of drawing them, and we'll add that step in next. Draw your single bonds. Always start with a single bond. Remember, multiple bonds are a last resort after you've run out of electrons. So if we do 12 minus 6, we have 6 others, okay? Oxygen needs 6, so we're going to start with our outside atoms first. There's 6. Okay, now I don't have any. Well, at this point, we haven't had to do anything else. Let's see. Is everybody happy? Hydrogen's got 2. That guy's happy. This hydrogen has got 2 as well. It's happy. Oxygen's got 2, 4, 6, 8. He's happy. Okay. Carbon, though, has got 2, 4, 6. It doesn't have 8. And we've run out of electrons, so what are we going to do? This is where we will now form a multiple bond. And what this is saying is we're going to change a lone pair of electrons from an atom that has a lone pair, and we're going to form a second bond. Why would an atom want to do this? Because it's all about energy, right? We've talked about how lazy atoms are. They want to be in the lowest energy possible. So if they have a lone pair that they can give to somebody else to form a double bond so that they can then have 8, that other atom can have 8, it's going to do that. So oxygen is going to donate this pair or any of the pairs of those lone pairs, and it's going to come right in here. We're going to show where they're going to move to. So we're going to redraw our structure to reflect that. So now when I draw it, the hydrogens have stayed the same because they were happy all along. But now there's a double bond in between carbon and oxygen. The other lone pairs, whichever ones you took, would still be there. Okay? And that's what our structure would look like. Now let's go through and see if they're all happy. We know where hydrogens are. They've got their 1 bond, their 2 electrons, so they're good. Oxygen still has 2, 4, 6, 8. Even though that 1 lone pair just moved its position, it still has 8 around it. Okay, and now carbon has 2, 4, 6, and 8 as well. Okay, so when we run out, again, as a last resort, atoms will donate a whole lone pair to form a double bond or even a triple bond if they need to. Okay, so it's the same process we've already done. It's just one extra little step. So if you feel comfortable, go ahead and try carbon dioxide and HCN on your own. And then you can replay the video and you can check to make sure your answers are right. If not, go with me and do this one with me together. Carbon dioxide, you guys should know is CO2. Same thing, figure out your electrons. 4 from carbon, plus 2 times 6 from oxygen. So that's a total of 2 times 6 is 12, plus 4 is going to be 16. So draw your skeleton structure. So carbon is going to be the center one. I'm going to have oxygens around it. Connecting those. Now, it's not going to stay in this structure. We'll talk more about why that is later in the next video. Subtract out those bonds. So there's 4. We've got 12 other electrons. 2, 4, 6. Oxygen's happy. 2, 4, 6. Oh, there's my 12. So I've run out. Is every atom happy? You can probably see, no, it's not. The oxygens are good, but carbon only has 4. So in this case, we have to form a multiple bond. You have options though here, right? Think to yourself, I've got all these lone pairs. Carbon needs a total of 4 more. Do you think it would be better for carbon to take, or for one oxygen atom to donate 2 lone pairs to form a triple bond? Or do you think it would be better for each oxygen to donate 1 pair and then form 2 double bonds? What do you think? Getting back to what I was saying up here, with this example, they want to use the lowest amount of energy. It's actually better for 2 double bonds to form than for a triple bond and a single bond. Think about it, guys. 6 electrons. What charge do electrons have? They're negative, right? Negative charges want to repel each other. So the more electrons you have in a bond, the harder it is, the more energy it is to keep that bond together. So our new structure is going to look something like this. Now, if you didn't have it drawn out like this, that's okay right now. Okay? We'll talk about it in the next video when we get to Vesper, why I drew it out that way. The big thing I'm looking for at this stage of the game, until we introduce Vesper, is everybody happy? 2, 4, 6, 8. That oxygen's good. Carbon's got 2, 4, 6, and 8. That's good. And then this guy's got 2, 4, 6, and 8 as well. So they're all happy. That's what our structure for carbon dioxide would look like, and we'll talk more about why it's like that in the next video. This next example, HCN, so we've got 1 plus 4 plus 5 for a total of 10 electrons that we've got to keep track of. This is the first example, guys, where we've seen hydrogen as the first element in your compound. Remember, don't get fooled. It can't be the central atom. Carbon's going to be our center atom. And then we're going to put H around it. Okay, there's 4 electrons. All right, so I have 6 left. Nitrogen needs 6 more. There we go. That's going to use all of the rest of my electrons. Is carbon happy? No, it's not. It only has 4. So where's it going to get those other ones from? Can it get any from hydrogen? No, because hydrogen doesn't have any lone pairs to willingly share. So it has to now get them from nitrogen. This is where we're going to actually form a triple bond, okay? Because there's no other way, there's no other place for carbon to get those lone pairs, to get those electrons, to get to 8, except for nitrogen. So when all the last cards, notice triple bond is the very, very last resort, okay, that's when it'll form a triple bond. So now our structure is actually going to look like this. But if you didn't have it drawn out as one line like this, don't worry about it. We'll talk more about why it's like this in the next video. Just make sure, again, right now, we're taking things one step at a time. There's 2 for hydrogen. It's all happy. 2, 4, 6, 8 for carbon. And then 2, 4, 6, 8 for nitrogen. So they're all happy there. Okay, so it's not really anything completely new. It's just one extra step from what we did in part 1 of the video. It's just now we can form multiple bonds. Now, this last step here, the last exception, are what are called polyatomic ions. Okay, so if we just break that term down, polyatomic, it means many atoms form a single ion. Okay, you have a whole list of these that you've got to be aware of, and when we get into our next unit on naming, you will You will get to see those, and we'll get to know those more. The good news is, guys, you don't have to memorize them. They're in your reference table, so you've just got to know where to look. The additional step, though, just one extra small piece, is that we have to account for the charge. Okay, so ions we know have a charge, so we've got to just account for that when we count our electrons. Okay, so it's really just something we do at the beginning, and then we continue the same process as we did before. So let's jump right in. Nitrate, NO3 with a 1 minus. Count up your electrons. So we've got 5 for nitrogen. Plus, we've got 3 oxygen atoms. Each has 6 that it brings. Now, we've got this new piece. Okay? Think back to what you guys know about ions. If I have a negative, what's happened to the electrons? Did I give one away, or did I take one in to make it negative? Answer is, I took one in. So that means we have one extra electron here now that we have to account for. So if it's a negative, we're going to add that to our total number. So it's 5 plus 3 times 6 is 18. So we're going to have a total of 24 electrons. Okay, so this last step here with polyatomic ions is just including this charge. If it was a positive charge, we would subtract that from this number. Okay, but because it's a negative, we're adding it into our total number of electrons. So 24, now I'm going to go through the same thing. Central atom is going to be the first one, so nitrogen. Put oxygens all around. Draw my bonds, my skeleton structure. So I've put in 6 more electrons, take those out. I've got 18 electrons left. So here we go, 2, 4, 6, 8, 10, I'm not counting right, 2, 4, 6, 8, 10, 12, 14, 16, 18. So those are my 18, I have 0 left. Now, is everybody happy? The answer here is no. Okay, oxygens, they're all good. But my nitrogen is the piece that's not okay. Now, you can go anywhere here. Look how many lone pairs you have to form a double bond. You've got a lot of options. And this is actually going to create something that's very unique and very important that you guys know this, this term. It's called resonance. Resonance is when you can have more than one opportunity to make a structure because of those lone pairs. So you can have more than one structure even though it's the same thing. So I'm going to just say, let's take it from here. I'm going to make it look like this. Now I realize there's not a lot of space here with this other practice example. So if you want to write it all out on a separate sheet of paper, that's totally fine. Or squeeze it in, that's up to you. So this is going to look something like this. Nitrogen in the middle, this oxygen's all going to be the same. This guy now is going to have a double bond over here. Okay. The last thing when you get done with your structure, you've got to include, with a polyatomic ion, you've got to put brackets around it, and you've got to include the charge. Remember when we did the Lewis structures for an ion, something like chlorine minus, right? And how some of us missed points on that quiz because we didn't put brackets or a charge with it. You've got to include that charge because that tells you, hey, you got this extra electron. If we didn't have that, we'd be 1 electron short and our structure wouldn't make any sense. So you've got to make sure with polyatomic ions, guys, that you put it in bracket form. Now, this resonance piece that I was talking about, what if I got it from right here? Okay, well, this structure would look something like this. It's the same thing. It's going to have the same bonds. It's just in a different position. Okay, so this would be nitrate as well. What if I did it from this oxygen? Okay, same thing. You can see how I'm kind of going around. They're all equal to each other. The double bond is just moving its position. Okay, this is called resonance, and it's a term you guys should familiarize yourselves with. I will almost guarantee you they will ask you that on the Regents. What is resonance? It just means the same structure, just multiple forms of the same thing where the double bond is moving to a different location. Okay? So, you guys go ahead and pause the video, practice sulfate, and then come back and check and see what it looks like. So, for sulfate, Okay, we've got, for sulfur has 6 plus 4 times 6 for the oxygen. Now again, this charge, if it's a negative charge, we're adding it. If it's a positive, we're going to subtract it. So 6 times 5 essentially is 30 plus 2. We've got 32 electrons. Sulfur is going to be in the middle. I'm going to put all my 4 oxygens around it. Connect all those. So there's 8. So now I've got 24. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. All right, I'm good, right? That's what my structure should look like. Is that it? No, you've got to make sure with a polyatomic ion that you include the brackets and the charge, because it accounts for those extra 2 electrons that weren't there originally. We've gotten those from some other place, and they're vital to our structure. Okay, so I know that's a lot of information in these 2 videos. Take some time, take a day or half a period or something like that, guys, to go through and practice drawing these Lewis dot diagrams. Okay, these are covalent compounds, so make sure you go through and practice those. Kind of do the first box as you're starting your work, and then over here is where your final, all right, your final one should go, like we've done with all the different examples. Okay, so do that. If you have questions, ask me in person.